Carlos Duarte. We are starting webinar, and I will ask my colleague Mario Arriola to start conducting the meeting. Thank you very much.
Thank you very much, Carlos. Good morning and welcome, everyone. This is Mario Arriola from the Mexican Space Agency, and I'm glad to introduce Mr. Paul Girdes from the TNO company, who's going to start talking to us about one of the main reasons for going to space, that is looking down to Earth. Please, Mr. Girdes.
Thank you. Thank you very much, Dr. Arriola. And I'm happy to be able to address this meeting, this group of people interested, especially in the issue of using space observations for support of the management of air quality. After having had many contacts in your country, in Mexico, in several fields, the Marine Science Institute of UNAM, the company Pemex, the tourist industry in Playa del Carmen, related to different problem situations. Now I'm happy that we could establish a contact with one of our senior principal.
Esta reunión está siendo grabada.
Research institute in the Netherlands, TNO, on the subject of satellite data for management of air quality. And therefore, I think we have gathered an important group of people interested in this subject. We had already some initial contacts, and they are with Semanat, with INEC, with UNAM. But I think it is good now to pick up again after some period of silence and to see whether we could finally develop this contact into a fruitful collaboration between the interested parties in Mexico and TNO in the Netherlands. And thanks a lot to the excellent organization by the Space Agency of Mexico and especially Carlos Duarte. So thank you, and then back to the moderator of this meeting. Thank you. Mario, your microphone is still off.
Thank you very much, Mr. Girdes, for your words. Now we have the message from the Director General of the Mexican Space Agency, Dr. Salvador Landeros Ayala. Please, Dr. Landeros, go ahead.
Good morning. Good morning here and good afternoon in Holland.
Thank you.
Netherlands. Welcome. I want to say some few words just to congratulate you for organizing this webinar. This is very important. The topic that you are going to discuss is one of the most important topics in the world in terms of science and technology. So you know that we are worried about the climate change and all the impacts this phenomenon produce in several activities or in several conditions like meteorology, like pollution, and those impacts also affects other applications like agriculture, like natural disasters, like floodings, droughts, fires, hurricanes, etc. So that is the reason, because this is very important. I want to say hello to the UNAM people, Dr. Cruz, Dr. Grutter, and all the rest of the people that are watching this webinar. Also the Mexican Space Agency people that is coordinating this webinar. And I think the opportunities are very big for the different participants. We could have collaboration from some Mexican universities that are working in this area, and probably with some companies in some industrial organizations. So the opportunities are very, very important. We have the intention to have another important project with the Institute of Atmosphere Science. So we after this, we could have some conclusions of the webinar in order to take actions, practical actions to have joint projects, joint programs in this area that, as I said, is very, very important, not only for Mexico, not only for the region, but for all around the world. Thank you very much.
Thank you very much.
Thank you very much for your words, Dr. Landeros. And now we have Dr. Xochitl Cruz Núñez from the Atmospheric Institute of National University of Mexico. Please, Dr. Xochitl Cruz, give us your message.
Hello. I am Xochitl Cruz Núñez from the recently renamed Institute of Atmospheric Sciences and Climate Change in Mexico, depending of the University of Mexico. Well, can I just share my display? I apologize for the Mexican presentation. I tried to explain in English. I would ask some help if there are problems. Okay, so let's talk a little bit about air quality in Mexico. Well, you know that mainly the atmosphere dynamics regarding chemistry in the atmosphere is referred basically on three processes. So the first one is the emission of certain compound that is released to the atmosphere, this very thin layer that is between the land and the space. Once the pollutants or any gas or any compound is released to the atmosphere, it is subject to several transformations that that here it is named as chemical or chemistry. Some compounds do not react in the atmosphere, some others do. And finally, these compounds that have been mixed, that have been reacted, that have been transformed, finally go back to the soil, to the surface of the earth as a sink. In terms of scales, the compounds can be scaling at different status. For example, in the atmosphere, this is the 0 to 10 kilometers, more or less, layer in the atmosphere. This is the closest layer of the atmosphere. There are some chemistry in regards with the compounds that have been released to the atmosphere. This is where the main reactions take place, and also the emissions are emitted in this layer. And we can see that the air quality problems and some of the emissions of the climate change are just taking place here. Then it is the stratosphere, where mainly the ozone is ozone takes place in terms of taking the radiation coming from the sun and capturing the ultraviolet portion of the electromagnetic spectrum. And then in this way, the life as it is in the in the earth can be take place. Finally, we have those compounds that they are not so reactive in terms of being subject of chemical processes, such as those related to climate change. For example, carbon dioxide, methane, oxide, nitrogen oxide, and the aerosols. Among them, we can find the very important black carbon. So this is basically the scale of these compounds. In the troposphere, the air quality is related basically to the pollutant criteria, the criteria pollutants, among which we can find the NO. NO is emitted directly from the different sources, transport sources, industrial sources, and so on. Then this NO is transformed as it is moving along the atmosphere. It is transformed to NO2. This is a normal pattern along the day in a urban place. You can find 6 hours, 8 to 24. So as NO2 is reacting, then the hydrocarbons react with this NO2 and finally form some secondary pollutants such as ozone, which takes place at about 12 to 2 o'clock, more or less. So this is one of the air quality problems, because ozone, as well as some other secondary pollutants, are of health concern, as well as landscape problems also, and so on. Well, this is basically the some of the family of the nitrogen compounds. We can find here the direct emissions as NO, but the family that is formed from this main emission is covered by many compounds such as NO2 and nitrates, NO2, N2O5, and so on, nitric acid, etc. So all of these problems are of public concern because of their toxicity, some of them, or because they are precursors of toxic compounds or air quality compounds. So in Mexico, the main research has been done in the Mexico City, and we have a record from more or less the 1980s. You can see, for example, here we find this is the concentration of SO2, sulfur dioxide, and in the lower graph we can see NO2 concentration trend from the 90s. Well, this is I can see well. Okay, so SO2 is a compound of health concern, but this is not as reactive as the nitrogen family compounds. This compound is important because it's part of the acid rain and also is a toxic compound, and was one of the main pollutants that was addressed in the reduction of their emissions from the 90s. We can see how here in the right part, this table is the emissions table, and you can see how the emissions in the Mexico City have been reduced along the time this is to 2006. And in the lower part, we can see how the emissions of nitrogen oxides have been reduced also, not at the same rate, but they have also been reduced along the time. You can see, you can see, for example, how high these concentrations in the 90s and main 20s, this concentration was of SO2, and the reduction is not as important in NOx. Also, we can find here in the left graph some ozone trend, the ozone trend, and in the right graph, the SO2. These are graphs for Mexico City, and these are from 1986. This is a historical trend from 1986 to 2021, and you can see how actually these concentrations have been just mitigated along the time. And this is also the particle, well, this is not the same trend in PM 2.5 on the left and PM 10. These are the particles a diameter of 2.5 micrometers and 10 micrometers. And you can see how this concentration along the time remains. This remains basically the same along the time. So there's a problem here that has to be solved, and also in PMT.
Ahora tiene un par de minutos.
Yes, thank you. Well, the monitoring sites in Mexico, there are some 90 monitoring stations along Mexico, the country. And you can see that the main monitoring stations are in the center of Mexico, but you can find that are huge spaces that are not covered by the monitoring stations. For example, we have here some, this is the Mexico City metropolitan area, the Toluca Valley, the state of Hidalgo, and the state of Puebla. And there are places where even when you find some monitoring stations, there are no meditions per se. So it is necessary also to cover the country, the whole country, mainly in terms of particles. Well, the greenhouse gas effect. You know that this is a very important issue, and you can find that the emissions in Mexico are about 600 megatons of CO2 equivalent. This is the main sources of greenhouse gases. This is wastes, the industrial processes, agriculture, and energy in the yellow graphs. It is important. There is a high uncertainty, you know, in aerosols, mainly the black carbon, which is important in terms of radiative forcing. And I would like to stress that it is necessary to get measures of the optical properties of aerosols, mainly black carbon, because this is a very important forcer of the climate in all around the world. And these are some measurements of black carbon in Mexico City. But we also need many other properties, mainly optical properties, in terms to be able to estimate several properties, for example, radiative forcing, the emissions inventory, and so on. And that's all. Thank you very much.
Thank you very much for your presentation, Dr. Xochitl Cruz. Certainly the chemical phenomena that take place in the atmosphere are very complex and very important to know and to understand.
Yes, indeed.
Now we have the presentation from the TNO company, and three of the main presenters, Mr. Anton Limhuis, Max van Strien, and Bas Heinzig.
Yes.
Go ahead.
Thank you, Dr. Ariola. Thank you for having us today. And yeah, thank you for organizing such a great webinar already. Let me share my screen with you. Do you see the presentation?
Yes, we can see it.
Good, thank you. Okay. If everything's working, today we're here with the three of us from TNO. My name is Max van Strien. I am a project manager at TNO Space Systems Engineering. And at my left is Anton Leemhuis, Senior Business Developer at TNO Space. And at my right is Bas Hensing, or Dr. Bas Hensing, Senior Scientist at TNO Climate, Air and Sustainability. And before we go into all the details about Earth observation, I would like to give you a brief introduction about TNO, who we are. We are TNO, and we are a Dutch independent technology organization. and our mission is to connect people and knowledge to create innovations that boost both sustainable competitiveness of industry as well as the well-being of society. And maybe some key facts about us. We are mainly about research and technology development together with consultancy. So we really give our partners and clients advices on how to tackle cutting-edge problems. We are independent, not for profit, and almost 80 years old because we were founded in 1932 and have an annual turnover of approximately €500 million. We consist of 3,500 employees, over 9 big parts of TNO, which you see to the right. I hope you see my mouse also, because TNO is way more than TNO Space and TNO Climate, Air and Sustainability. We also look into IT, traffic and transport, the energy transition, all relevant topics you can think of. I think TNO does something on it. And we really look into creating the bridge between cutting edge technology and the industry. So really seeing, okay, what is the need and how can we push the boundaries, making the impossible possible. And that is how we love to bring technology into practice. A bit more specific. TNO Space and Scientific Instrumentation has 4 main objectives which really support the Sustainable Development Goals as set by the United Nations. The first one is to prevent climate change and air pollution using Earth observation satellites. The second one is enabling secure broadband connectivity using optical laser satellite communication technologies. The third one is to help understand the universe by both the design and the development of new high-tech telescope mirrors and systems to calibrate ground-based telescopes. And finally, we also want to stimulate economic growth in both the Netherlands and the European Union. However, we also have strong worldwide partnerships, as you will hear more about in just a minute. And we, of course, are going to go more into detail into preventing climate change and air pollution. In front of you are people of 2 departments within TNO. We have special, or like Anton and me are from Earth observation, where we develop and design satellite instruments and have almost 40 years of heritage with that. We do the instrument calibration in-house, but we don't only create the instruments, we also look into, okay, once the instrument is in orbit, how can we use the data and how can we use it to create a better world for each other? And Bas Hensing is from Climate, Air and Sustainability, where they look into atmospheric modeling and use the models they create to give advices through which policymakers can really reduce global warming, increase air quality, preserve nature, and also stimulate economic activities. Now I would like to give the word to my colleague Anton Leemhuis, who will go more in detail on the value chain at TNO.
Good morning, everybody. Thanks for the opportunity to speak here. My name is Anton Leemhuis, and in TNO, I'm responsible for the program for the development of Earth observation instrument, as well as the data utilization of this. It's a pleasure to speak to you today on Earth observation instruments and how we use their data. And to give you an idea what TNO's position is, I show you here a value chain. Basically, the issues that we address here start with emissions, as was so nicely illustrated in the previous presentation. TNO has a lot of knowledge on emissions because we are in the Netherlands, the organization that makes emission inventories for the Dutch government, and we do a lot of research on emissions. Furthermore, we use satellite data to better pinpoint where emissions occur and to quantify them. Emissions are then transported in the atmosphere where the chemical process that was outlined in the previous presentation occurs. TNO has a lot of knowledge on chemical transport in the atmosphere, and we develop our own modeling software called Lotus to characterize this. The next important step to take is not to only predict what happens with emissions and how they're transported, is to monitor it. TNO is active in that field, both on ground-based measurements and verification, and using satellites for this, which we will talk about more in this presentation. Now, the ultimate goal of all these monitoring activities is to have better measures to reduce emissions. And this is where we come full circle. So better modeling and monitoring of emissions and chemical transport, we advise policymakers on what the effective ways are to achieve the reduction of air pollution and greenhouse gas emissions. Now, we do that with a very large different amount of partners. A very important one is the Copernicus Atmosphere Monitoring Service of the European Union. TNO is involved in a lot of technology projects for them, but also in the operations of the CAMS system. So every day in Europe, the European Air Quality Index is calculated using TNO models. But we also work for the German government, for the Dutch government, directly for the European Commission, and industries like ESA and Airbus. If we look at the role of satellite observations, they are very specific. So in order to monitor air pollution, the most precise measurements available are reference stations. They are typically container-sized, and they happen at limited locations in the country. In addition to that, in the Netherlands, we increasingly do community-based monitoring, which are local sensors that are less precise and are particularly valuable in cities where you want to have a better idea on the concentration of pollutions in certain areas of the city. For example, particulate matter and carbon dioxide. Then there is the satellite, which is a third important tool that has unique spatial coverage. So the satellite shows you the concentrations of air pollutants in a very big area in the country. Moreover, it provides typically global measurements. So you can also have an idea about pollution, how it travels into your country and across borders. TNO has a very long heritage in developing such instruments. Today we'll talk, for example, about Tropomai, the instrument that was launched by ESA in 2007 and currently measures air pollution and methane globally on a daily basis. That instrument was designed by TNO, partially built by TNO, integrated by Airbus, and flown by ESA. Currently, TNO is working on the successor of Tropomai, which is Sentinel-5, which will soon be launched. And we worked on the predecessor of Tropomai, called OMI, as well as other important instruments before that, like Skiamagi and Gome. So TNO has a long track record in this area. We also work on new cutting-edge innovations, and that is to shrink the size of satellite instruments from, let's say, this size to this size. So you can fit them in CubeSats, which are 10 times as affordable as the classical and 20 times as small. Here you see the Spectrolite instrument, which is about this size, and that can fly in a CubeSat. And we have flown the instrument in an aircraft in Germany to measure emissions of power plants. In this movie, you will see how we plan to use it in a space mission.
The Paris Agreement aims to reduce man-made greenhouse gas emissions and control climate change. But the true extent of emissions is uncertain because they are not effectively measured. Global observation satellite missions will help quantify and verify emissions. The Tango mission, with its 2 small satellites, will complement these global observations by zooming in on targeted emissions. So carbon quantifies CO2 and methane emissions. When the Tango satellite targets a selected emission source, forward motion compensation extends the observation time and boosts measurement precision. A spectralite instrument measures the plume, and raw data is relayed to the ground, where it is processed into quantified emissions for use by scientists, policymakers, and the industry. Tango's value lies in its open data policy and the ability of users to flexibly choose targets. It will provide complementary data with high spatial detail to the global survey of the Copernicus CO2M mission. Tango's unprecedented emission flux precision increases the number of detectable targets. And Tango will allow for the collection of 2 years of precursor data to the CO2M mission. Tango uses mature technology and a modular CubeSat concept that can be developed quickly and affordably, which allows it to grow into a constellation with expanded and monitoring capabilities. A team with more than 30 years' experience in atmospheric remote sensing are behind Tango and will put man-made emissions under a magnifying glass.
So in this movie, you saw a glimpse at the future on how we want to push the boundary of measuring air pollution, greenhouse gases at facility level in the future. The Tango mission is currently going through development within the European Space Agency, and I'm happy to say that we recently secured a significant contract for the technology development of it. And at the same time, we are working on partnerships to launch it, hopefully in 2024. Now, back to the present. What can we do with satellite data that's currently available? It really depends on what problem you want to address. And the two main problems of interest today are air pollution and climate change. On this slide, I have summarized the most important capabilities of satellite systems available today. If you look at the three main capabilities, it is firstly the improvement of prediction models that are generally used to predict climate change and air pollution. So satellite data can be used to improve those models. My colleague Bas will say more about that in a minute. Well, in addition to that, we can directly use satellite data to quantify emissions. This works in particular well for nitrogen dioxide, sulfur dioxide, ammonia, carbon monoxide, and methane. For CO2, there are some possibilities, but that is still quite challenging, and we have to wait for the new generation of satellite systems in orbit to really start working on this. For the measurement of surface concentrations, there are also possibilities, especially for nitrogen dioxide, aerosols, ammonia. There are strong capabilities currently available using the Tropomai satellites, but also other satellites like the CRIS satellite of NASA and NOAA. So depending on what problem you want to address, satellites provide a diversity of solutions already today, especially to combine them with ground-based measurements and models. And for the case of Mexico, I would say, the areas that you currently have in your country with limited ground measurement capabilities, I think satellite data can provide very nice additional measurements and insights. In particular, for the challenge that you will see there is that satellite data is publicly available. So, for example, Tropomai data, you can download it for free from ESA, but it takes a lot of knowledge about atmospheric physics to interpret it correctly. I give you an example on this slide. Here you see on the top right-hand side the methane data of Tropomai before we do a basic filtering and quality check on it, and after. So after we do the quality checks and the corrections, you get the result on the right hand bottom. So what you see is that just looking at the raw data is not enough. You need a lot of knowledge on emissions and atmospheric physics to transform the raw data of these instruments into useful information. And TNO is in a good position to do that thanks to our knowledge of atmospheric chemistry processes, our knowledge of emissions, and because we designed the Tropoma instrument. So we know the instrument very well, and we work with the science teams who developed the latest retrievals for it. In this case, the methane retrieval, which is developed amongst others in the GILS consortium in the Netherlands. An initiative that I would like to highlight to you that could be of interest in Mexico regards the quantification of methane emissions. I saw in your presentation that the energy sector is an important contributor to greenhouse gas emissions. In the oil and gas, for example, we see methane emissions typically playing a large role. TNO is currently setting up an international cooperation between oil and gas companies to use the Tropoma satellite instrument to improve the detection of methane. If you are interested in that, let us know and we can follow up on that later. This work is based on success stories we worked on in the past. For example, the measurement of a blowout in the United States, but my colleague Bas will tell more about that in a minute. So this gives you an idea of our background, what our position is and what we're working on, and what problems we could address with satellite data. Now we will dive into a few practical examples of specific gases that are measured with Tropoma, and my colleague Bas will take over. Thank you.
Thank you, Anton, for the introduction. Let's first look at a movie.
Limiting climate change and air pollution is perhaps the greatest societal challenge of our time. In order to take effective measures, we need to have a very good grip on the relationship between emissions, atmospheric processes, and concentrations. Emissions are now dominated by human activities. In addition, there are emissions from natural processes, such as wind-blown soil dust and the metabolisms of plants and animals. Concentrations of substances are determined by different processes. The emitted substances are dispersed in the atmosphere by diffusion and are transported by the wind. Some substances undergo chemical reactions in the atmosphere. Eventually, many substances are removed by rain or by adhering to surfaces. This is called deposition. The Lotus Uros model takes all of these processes into account. The important inputs for the model are emissions of substances, land cover data, and weather data from weather models. At a resolution varying from 1 to 25 kilometers, concentrations and deposition are calculated per hour. In doing so, we can gain insights into current and past concentrations and deposition and make forecasts. We can also perform scenario calculations in which the impact of climate change or emission reductions can be determined. The model is validated by using ground and satellite observations. Using data assimilation techniques, these observations can also be combined with model calculations to immediately improve the model result. These comparisons with observations contribute to the further refinement of the emission input and to the improvement of the representation of processes within the model. This process reduces uncertainties so that we can determine more accurately which emission sources make the largest contribution and provide a reliable air quality forecast. The model is being developed continuously. By using the most up-to-date knowledge and data, we provide important information to policymakers, citizens, and businesses, and we find an answer to cross-sectoral issues. In this way, we can identify measures that contribute to a healthy society, and we can work together to create a cleaner environment.
This was a movie about Lotus Uros. Lotus Uros is our air pollution model or our air quality model. And it treats all the processes that Professor Cruz introduced in your slides about the emissions, chemical transformation, the transport, and finally the endpoint. Does it go to the surface or is it reacted away? So looking at these clouds moving over your screen, it's not a weather model that says where do the clouds go with the precipitation, also predicting the wind direction and the temperature. Our model predicts concentrations of greenhouse gases and of air pollutants in the atmosphere. It tells us where it goes to the ground in cases of nature protection areas, for example, or where it is removed from the atmosphere. Our model treats particulate matter, ozone, NO2, SO2, basically all the species that Professor Cruz was talking about. So who is using this model? This model is used by ourselves, for example, for the ocean prediction in the Netherlands. Anton Leemhuis already told us that we use it in Germany, for example, calculating the depositions. But our most important user, as also already explained, is the Copernicus Atmospheric Monitoring Service. And that is the European answer to the request, or I should say the need of the people, the industry, of the governments, to know about the air pollution levels and rules responsible for it. When I talk about our model, Datos, I say our model because we developed it in 20 years and we used about 200 man-years to finally make this model available. But it's not our model alone. We have a great international user group that also developed this model from now onwards because our model is open source. Looking alone at the Netherlands, a small country, only a few hundred kilometers wide, we have already a lot of users. Some 20 people are continuously using our model to do scientific research at the university, develop in detailed processes how ozone is taken up by the crops and how the crops are destroyed depending on the temperature. And every single academic user is improving a small part of the model. But on the other hand, we have also the industry that finds new applications of the model output, so the concentration level, for example, in new areas where we did not use it before. Zooming a bit out, we see our users in Europe, and we see also, again, academic users and also industry working together in the Copernicus Atmospheric Monitoring or for their local governments. And zooming out even more, we see a few of our users worldwide. For example, in Colombia, we have a big academic group of mathematicians that develop data assimilation systems where we can use observations from space or from the surface together with our chemical transport model, our air pollution model, Datos. Another initiative, for example, in Southern America, also in Chile, where we work together on harmonization the emission inventories. Because as was explained before, emissions are crucial to finally know how much pollution is in the air. So why do we need this Datos? So we know what it is, we know who's using the model, but why? I mean, if I look at the three first points, evaluating trends, for example, if we look at a map of CO, carbon monoxide fields, for example, and taking an average of 3 months and do that for the last, well, what did we say, 40 years, we see the trends. We see how things are changing now. And also if we look at the different seasons, we can see how the biomass season is changing in time from year to year, or where the crops are burned. We also can use this information to have an emission estimate top down. So not calculating how much fuel is consumed, but looking from the space down to the surface and say, this is the total emission in this area. Also, we can do direct satellite monitoring by just looking at volcanic plumes and saying, well, this is a hazardous area. You should not fly here. So direct satellite-based monitoring is something we do a lot. But still, we need this model in quite a few cases. Why is that? For example, the first one is continuous data. If we look at Trachomai, it flies over every day, worldwide. Every location of the world is seen. But if there is a cloud, there is no surface observation, and we don't see our particulate matter or NO2 columns. Also, I saw the picture of the NO2 in the early morning and the ozone peaking in the afternoon. If you have only one observation, you do not see this daily cycle. We need to fill that gap with our models. Just to give you a few examples, and later we go in more detail. Another important point that we will come is the source apportionment. If we see a total bomb and we know there's a lot of pollution in the air, we do not know who was responsible for it, what source is responsible for it, or what area was responsible for it. This is what we do with a special case of our Lotus model, and it's our labeling tool, TOPAS. To go back to our examples, this is the blowout of the methane from an accidental release. And we had this overpasses of tropomine day after day, seeing huge concentrations. And then we want to estimate how much of methane is emitted from that source. And to put it simple, we just say, well, we know it's a big one. For previous source in 2015, we also knew what is a big source. So we just say, here, there's a big source. In our model, we release the emissions. We know how it's distributed with the wind, how it's mixed in the vertical, and it predicts the concentration. We compare that concentration with the observation from space. We see, whoa, they're not quite the same. Oh, indeed, the emissions should be higher to have such a high concentrations. So an automatic data assimilation system matches the observation and the simulation finally, and reads back the emissions that were initially responsible for reaching such a high concentration. In this way, we could see that this was really one of the biggest emissions that were measured in time, just by looking from a satellite downwards. And this is now applied not only for methane, but also for many other sources. Another example is on sulfur dioxide. We've already heard that sulfur dioxide is harmful on itself when you breathe it in, and also it causes acid rain, so it destroys crops and forests, for example. But sulfur dioxide is also very important to monitor for another reason. Not only here, we have one picture, we see 1 hour of data of tropomine, and you see it's quite empty because we deleted all the data that didn't contain all the relevant information. This is the first step we added after downloading the data. And then you see there's only a very little amount of data left. You recognize maybe the western part of South America. So on the northern part, we see Colombia with some colors. I try to move my mouse here. And if you go down, you see Peru. And there's another emission source, that's the Sabancaya, that's a volcano. If we zoom in a little bit more, and we see that there's a lot of, concentrations, but we do not know anything about emissions. But I already told you, we can estimate now the emissions from just looking at the concentration by adjusting emissions until we reach what we have. And this is not only nearby the source, but also further away, because what is present here was released a few hours before. In this way, we can estimate the emissions 24 hours and also the emissions of yesterday. And if we do that for a little time in a row, we see sometimes big changes in SO2 emissions. And this is very strongly related to pre-eruptive degassing. So just before a volcano is going to erupt, it releases a lot of SO2. So this is really, really useful for early warning system. Another application concerns the Middle East. In the Middle East, we have a lot of gas winning and oil winning. And with that, there is not only methane releases, but also a lot of SO2 is emitted. The SO2, in the past, it was also in the fuel. That's why we have very high SO2 concentrations in the city, for example. By taking out the SO2, we don't see that back. And as Professor Cruz showed us, we see a big reduction in SO2 in the cities. But this may not be true everywhere in the country. For example, here in Saudi Arabia, this is the big central country shown on the screen, we see that in the main cities that are there, the SO2 concentrations go down, but not the ones that are very close to the coast. And I have very difficulty with mouse, but here also there are very high concentrations. And now from the concentrations, we can calculate backwards what were the emissions. But what is more important, we see a lot of places where there is no point source known, because the black points, the black squares are the point sources. And here we see a lot of concentration, but we didn't see any point source that was known. In this way, it helps us to identify where the known point sources are. And this can be because there's some activity that was not mentioned, but it can also be that there is a leak. And this is also very important because our final air pollution concentrations do not only depend on the wind, so on the meteorology, but also depend on the emissions. So this also helps us a lot. So we have from the volcanoes, we have from the gas winning, and if you then look at a larger picture of an initiative to see what kind of sources do we actually see, and this is one of the sources that we can very clearly see with Trapomai, concerning power plants, volcanoes, oil and gas winning, and smelters. Looking at another example, we do have the central picture with Trapomai, the satellite. It's the second picture, and on the bottom you see a perfect drawing of a satellite. And left of that, there's the model. So that is Lotus Zero's output. And those two look alike a lot, because for the Netherlands, it's a small country. We have a good view of where the sources are. But still, there are differences. Some sources are collected on a yearly average, but then distributed in time, distributed in space. It's a big challenge. And that is where we use the data assimilation. So if the model predicts a value like here, and the satellite predicts some other value, we have to find the optimal value, taking into account both uncertainties. And by doing so, we do not only modify the concentration itself, but we make use of all the information of the emissions that were responsible for that final concentration. And this, you can understand, is a very big mathematical question that has to be solved. And that's why we developed that with a lot of technical universities and fundamental university research. And now we have a system ready that can do the data assimilation, where we can just everywhere in space the emissions to finally have the best optimal result from the model and the satellite. And then on the right, you see the relative difference. For example, in front of the Dutch coast, there were some higher concentrations measured by Trapomai. That's why the relative difference is a bit red. We have to increase a little bit the analysis. Our model was too low. And over Germany, you see the same. But over a large part of the Netherlands, our model was a bit too high. So we had to adjust downwards. And the final product is then optimized.
Max, you have 2 Minuten. 2 minutes, please.
Okay, thank you. So this is another example over India, where we have a model that is on coarse resolution, but the satellite observations are much higher resolution. And we can see, for example, where to optimize our monitoring network, because there are some areas where we have clouds, so there are no observations from space. There you want to do a measurement, because the model calculations are there. But other areas, we see that the model predicts no high concentration, but the concentrations are really high in the valley. So in this way, we can detailed look at this picture. We can see where we should add measurements. The next slide, I think I have to give it back to Max.
Yes. Yeah, that actually brings us to the Topaz demo, which was a separate part of the agenda. Am I correct?
Yes, that's right.
Yeah, so is it okay if I continue? Because that was 5 minutes, right?
Go ahead.
Okay, then that brings us to Topaz. Thank you, boss. So you see a slide here with a map of Europe to the left and a lot of data. One of the outputs, or one of the things that my colleague Bas already mentioned, is that we can label emissions using our Lotus Zero's model. And we have the TNO operational pollution apportionment service, which you can just visit online. It's at topaz.tno.nl, and it's for the entirety of Europe, for a lot of the big cities. And using the output of the Lotus Zero's model, it can give you the country and the sector contributions to particulate matter below 2.5 micron and below 10 micron. But let me just show you. This is the website. I hope you also see the website popping up. Do you see the website?
Yeah.
Yeah. Okay, good. So if you go to topos.tno.nl, you just get this website and you can just check it out, how it works for all the major cities within Europe, all these little dots here. And you can select particulate matter below 2.5 micron or below 10 micron. But for the example, let's do all particulate matter below 2.5 micron. Anton, Bas, and I are currently in Utrecht, the red dot here in the Netherlands. It's approximately in the middle. And what Topos does, it gives you the last 6 weeks of particulate matter concentrations in the air above Utrecht, and it gives you 2 graphs. Every bar is a day. So this is for August 17th until, yesterday. And you see the different country contributions to the particulate matter in the atmosphere above Utrecht. And you can already draw quite some interesting conclusions from this. You see that, for example, from August 26th to say September 1st, there's quite some light blue. The overall concentration is quite low, but there is quite some sea salt in the air. So most likely the wind is coming from the sea, which is from, if you see Utrecht at the map, most likely from the northwest. At the other hand, if you look in the period from September 6th till September 10, you see that there's way more particulate matter in the atmosphere above Utrecht. And you see that white and purple are quite dominant. And white is Germany, Deutschland, and purple is the Netherlands. So most likely there is weather conditions or different conditions in that day. So most likely the wind is coming from the east over Germany. That's country contributions, but it also gives sector contributions at the same dates. And here again, you see, well, for the lower concentrations, it's again sea salt. But for the dates where we were just discussing that there is a lot of particulate matter coming from Germany and from the Netherlands, you see that there is purple and yellow are the biggest contributors, which is agriculture and road transport, which is quite interesting to see and also gives you quite an idea of where the particulate matter in the air is coming from. Maybe to just give you a random other city to show you that it can really change per city. Let's say one a bit far away, let's say Nicosia, which is more to the south. And then you see that there is way more sector contributions from energy and from industry, the green. So it really gives you a lot of insight for actually a lot of cities and observation points in Europe where particulate matter comes from and what is the origin of it. So feel free to look it up, topos.tno.nl. You can always access it and just see what it does and what has happened the last 6 weeks in Europe. So that was the demo. And I would like to wrap up briefly with one last slide. In summary, is that we as TNO support governments and industry to make informed decisions about both greenhouse gas and air pollution emission reduction. And I want to emphasize 2 things. We have a leading position in air quality and greenhouse gas emission management. We have this position in the full value chain as explained by my colleague Anton, and we work with national governments, the European Union and the private sector. We have 40 years of heritage in both designing and building satellite instruments for big organizations like ESA and NASA. And my second point is that satellites really provide independent and global monitoring data. Possibilities vary per species, but we can measure it for quite some species, as you can see on the slide. Satellites can detect big hotspots and can quantify large emission sources independently, but improved prediction and forecasting can be done using chemistry and transport models like our Lotus Euros model. That being said, that brings us to the end of the presentation. Thank you for your attention. Thank you for having us again. And if you have any questions, let us know later in the question moment or contact Anton Leemhuis at the following email and phone number. Thank you very much. I'll stop sharing.
Thank you, Max.
Thank you very much.
Thank you very much. My video is muted. No pueden ver video, chicos.
So now we will start with the Q&A session. So if there's any person in the audience within the this Zoom video conference meeting room has a question, please, the floor is yours. This has been a wonderful webinar. And we also have questions from our YouTube audience. But please, is there any question from our guest from the Mexican Space Agency, Dr. Salazar? No question?
There is a question from internet, Carlos, from Ricardo Miranda.
Go ahead. Could you open your video, please, Mario?
Yeah, it's open. It's open. It's open.
Okay. Thank you.
How can we validate your satellite models if Mexico didn't have quality surface data?
Yeah, the question was, how can you validate the satellite product when there's no high quality data available at the surface?
Yes.
Is that correct?
Yes. For Mexico.
Yeah, for Mexico. That is the good thing. We have a lot of areas that was shown by Professor Cruz where there are not a lot of observations, but the satellite instrument is sensitive everywhere the same. So the product is harmonized. So the areas where there are no observations or the observations are not high quality, they can lean on what they learn in the other areas. And there are 100 observation sites in Mexico. And that means that there is enough data to actually say something about the value of how to connect the satellite data to the service data. It's not one-to-one. The satellite data sees a total column, and the observation sites are at the ground. You need something to translate the total column to the surface concentration. That's where we normally use a chemical transport model for an air pollution model. But the information of the 100 points that are available are normally, even if the data is not the highest quality you hope, is already in practice enough to say something about what is happening elsewhere. So I think the data availability looks quite good.
Thank you.
Well, I have a question, if I may. Well, first of all, I would like to introduce Dr. Rosa Maria Ramirez de Arellano. She's our General Coordinator for International Affairs and Security at the Mexican Space Agency. And we just had a meeting this morning in Mexico City at 6 a.m. with the guys from SCO, from Space Climate Observatory. So this webinar is really important for us, for the Mexican Space Agency. Considering that we have many pollution issues in Mexico. And also I would like to introduce Dr. Adan Salazar. Adan, could you open your video, please? Adan is our... Dr. Adan Salazar is our General Coordinator for Scientific Research and Technology Development at the Mexican Space Agency. So he's a very important person at the Mexican Space Agency in terms of interacting with TNO. And I also, let me see, Dr. Victor Garcia Garduño. He is the director of our research center in the state of Mexico. Our research center at the state of Mexico is located about a 2.5-hour drive from Mexico City, and it's currently starting operations. And one of the areas of this center related to this webinar is using space data, space images, processing of space images for different applications like agriculture, etc., health, air pollution, etc. So Dr. Garcia Garduño is here. And hi, Doctor. And also we have at this center, there's another operation, which is the development of a small satellite. So I see that there could be some relationship or partnership with TNO in the development of optical instruments. And I will talk more later about this when in the conclusion. So I don't know if there's questions or comments.
Carlos,
yes,
is Adam speaking. Yeah, Dr. Michael Grutter has his hand raised, so I think he can add more or give some comments to this presentation, or are more questions to Max that present about the climate change, air pollution. So I don't know if we can give him the right to speak.
Yes, of course.
Hello.
Go ahead, Michael. Could you open your camera, please?
Yes, thank you for, I just had a question with respect to the presentation. Thank you very much for a very nice presentation, the people at TNO. It was very interesting. You showed very impressive plots of methane emissions. I don't remember which region of the world, but you mentioned the importance of data treatment using raw data and then doing some quality assessment of this data. Could you give us more information about what kind of data treatment you did for assuring this quality of the data that you showed? Is it more with, having to do with cloud filtering, or is there something else?
Yes, there are various steps to that. First of all, you have to look at, let's say, the quality of the data product on a pixel by pixel basis. And clouds are absolutely a factor that have a negative impact, but there are many more. Aerosols are an important one, and they can lead to a direct, let's say, poor quality of the observed pixel. Now, those you can filter out. That is fairly straightforward. But still, you have to know what you're doing, because it's a gradual scale from excellent quality to poor quality, and a lot of things in between. Then there's other effects like the albedo. I guess you know what the albedo is, but for the people in the audience who may not know, let's say it's the brightness of the surface. That also has a impact on the methane product. Then there's even more factors. There's the elevation of the terrain that can also have impacts. Are you in a mountainous area, or are you in a flat area? Another factor you have to start looking at is the wind speed. And if you want to assess the wind speed, you have to take into account, are you looking at momentary data? So let's say a snapshot of a single moment in time, or are you looking at the average over a few days or a few weeks, and the wind direction may change? You have to correct for that. So you have to correct for the meteorological conditions. On top of that, it often helps to know what you're looking at. So it really helps to have an understanding of the emissions on that location. And there's often knowledge available on that, either in scientific literature or public databases, and they also have to be interpreted. So there are many different levels of, let's say, modeling, filtering, and processing of data that you can apply to go from a crude image to a more informative image. And that is even before you start doing more advanced modeling with chemical transport models that can add an additional layer of information to your image. So that just to give you an insight in the type of treatments you need. Last but not least, unfortunately, there is never a single product. For methane, the Tropoma product that you can download from the ESA website is now the current formal product. It's a good product, but new versions are being developed that are even better. Because since 2017, we are doing continuous campaigns around the world with aircraft, with ground-based measurements, with LiDARs that look into the atmosphere to make better products. And these new products are made available only every now and then, let's say once a year. And that means that there are newer versions of products that not everybody has available yet. Luckily, we have them. So we have the luxury of also looking on a case-by-case basis if improved products are available. So that's all the know-how that goes into this filtering. Does that give you an answer to your question?
Yes, thank you very much. I mean, we do satellite validation. We participate in international validation efforts also for methane. There's an article that just came out. We have some stations looking at column, not only methane, but NO2 and things like that. So, but with the things that you tell us, I mean, it's quite clear the amount of effort needed to have a level 2 or above product.
Yes.
Just a question would be, these new versions you were talking about, is it possible to have access to them maybe by collaboration or something like this?
Yes, through collaboration. So not public, but we can discuss that. So if there's a collaboration between us, then we can see what we make available for that. Absolutely. So that's on the level 2 or the level 1B product. And also for, let's say, the level 3, level 4 products where more models are involved, we can also collaborate on that.
Thank you very much.
And I would be highly interested to read your paper. So if it's already published, if you can send a link, that would be nice.
Okay. Thank you.
Any more questions?
Yes. I see a question in the chat. Shall I try to answer?
Yeah, sure.
In the chat, I read, I want to know about the Lotus Euro system, what meteorology is used, as well as the chemical mechanisms therein, and also say something about black carbon. So I will try to do all three of them. Meteorology, most of the time, depending on where we are, we use the European Center for Medium Range Weather Forecasting. It's called ECMWF. So the European Center for Medium Range Weather Forecasting. That's a global project, so it can be used everywhere. That is nice to have direct access to data. But we have also higher resolution local data. For example, for the Netherlands and Germany, we have access to something that is a high local product of the local meteorological offices in Europe. For example, it's called Harmony. It's one of the models. We have also access to another model, Cosmo, and there are all kinds of interfaces to be able to use different meteorological data. So also what is an open access data for meteorological model is the WRF. Sometimes people say WRF. Yeah. It is a meteorological model that is also used by many, especially academics, because it's an open access data. You can start with it, but it's the problem is that it's an open source model and everybody can push the button play, but you do not know the result. You need to be a real expert to have good outcomes. And if you have a PhD student or somebody who's working with the data for 4 years, then you finally have something that is good. And I'm sure our model will run with your local meteorological model. That is not an issue normally. And the chemical mechanisms therein, to be brief, everything is there. That's the easiest answer. So the formation of the ozone, the formation of all this nitrogen chain that Professor Cruz was talking about, that is of course solved. There's also a specific VBS system for the organic compounds related to barbecuing and smoke, stuff like that, because there are a lot of different organic species and they should be sunned to finally make it handleable. That is, that is also included in the model. So the production also of the secondary species that are not originally emitted, like ozone, it's formed in the atmosphere, as was explained by Professor Cruz, but that also concerned the formation of secondary organic aerosols and secondary inorganic aerosols, like the ammonium nitrate I saw in some slide, but also the organic carbons. That is also in the model. To say something about black carbon, personally, I'm in the European working group to develop the European standard. So we have a standard method how to measure black carbon in the atmosphere, and it's measured as an evolving carbon method. It has a thermal optical protocol for the INTIMI here in the audience. So it's elemental carbon, it's called. It measures OC, organic carbon, and elemental carbon. But now in Europe, we're on the way of producing also a new standard for equivalent methods that do not measure elemental carbon, that measure another component of black carbon, because black carbon has 4 different properties. It's refractory, that's called EC. It's absorbing light, that is called equivalent black carbon, with absorption photometers, for example, like the MAP, the etalometer, the PSAP is sometimes used in the Northern Americas. There are different absorption photometers that really measure the light absorption of black carbon. And there's now in Europe an activity to do the equivalence testing. So does this standard, elemental carbon, how does it compare to other measures of black carbon? So if you have different measurement equipment in your network, you can still compare them. And that is a very difficult task, and that's why I understand the question so well. In Europe, we have now finally one harmonized system, and we already, if you want to compare modeled outcome with a measured outcome, that causes headache, pain in the head, because it is very difficult. What you model is mass, what you measure is light absorption. How do you do that? We think we finally know how to do it. I hope this answers your question.
Okay, I have a question that I posed on the chat. What will be the effect of solar flares on the performance of your instrument and its measurements?
So here I assume you're mostly talking about radiation levels, and yes, obviously it depends on the instrument. Now, if we zoom into the Tropomi instrument that is used in most of the examples, that is designed to be able to handle all kinds of circumstances, including solar flares, and solar activity goes through cycles and can have eruptions. And the Tropomi instrument is on an ESA satellite, so of the European Space Agency. It is part of the Copernicus program in a Sentinel mission. And these are satellites that are meant to provide operational data products. So they have to be very reliable. So they are well designed to be able to handle that.
Thank you.
I have a question.
Carlos.
Yes, I have a question regarding the Tropoma instrument, and my question is, how the Tropoma instrument compares with the GeoCarp satellite that NASA has been announcing to launch in the next years? I know the GeoCarp is a geostationary satellite, and Tropoma is LEO. It goes into LEO orbit. But besides that difference, what can you say about spatial resolution, for instance, and other features? Do these two instruments complement each other? Do they compete? What's your point of view regarding the GeoCarp satellite?
Yeah, I think they are in principle complementary instruments. GeoCarp is, as you say, geostationary, and it roughly looks at North America. And Tropoma is a LEO instrument that covers the globe. So in terms of coverage, they are complementary, but overlapping in North America. What is nice about GeoCarp is that you will get real-time view on the continent, which is very nice to detect, for example, emissions. During the emission cycle in the day, the spatial resolution is different, but I would say not fundamentally. They are both multiple kilometer pixel sizes, so one will not give significant benefits over the other. It's not that one of them has sub-kilometer pixels, which I think is the real game changer you want if you want to look at emissions, and both are very well suited to measure gradients of the large sources. I think in terms of instrument philosophy, there are different types of instruments, but they both rely on the fairly high spectral resolution to resolve spectral features. So in that sense, they're similar. If you look at the data products, GeoCarp is there it goes again. GeoCarp is predominantly a greenhouse gas monitoring mission, whereas Tropoma is a air quality mission. So Tropoma gives you a wide range of air quality products. And I think one of the really nice features of it is that Tropoma uses the heritage of Skiamachi and OMI, and has very well validated data chains and products that are tested globally. So I think that's very nice. GeoCarp will be a game changer because it will also have CO2 measurements. And as I said in my presentation, there's currently a lack of those measurements. So for the Americas, the CO2 product of GeoCarp will be, I think, an enormous game changer. In that sense, I think the European equivalent of that will be the CO2M mission, which is the upcoming Copernicus mission that will measure, just like GeoCarp, methane and CO4 at roughly the 2 by 2 kilometer pixel that a GeoCarp will also offer. So I think in that sense, they're quite nice complementary data sets. I know that NOAA and NASA are looking to replace their GUSAR geostationary satellites with the GeoXO mission. I think that will provide the geostationary instrument of the Americas that will provide similar products as Tropoma, but that will take many years before it becomes operational. And I think we have to keep our fingers crossed that the US government passes its next budget so that the studies of that instrument can start. So think there's still a journey ahead. So in the meanwhile, Tropoma and Sentinel-5 for air quality, I think, will provide a very rich information source.
Thank you
Does
very much.
An ID?
There is a question regarding the height that you can measure the air quality or contamination levels. How high can you measure?
How high you mean? What levels it can measure?
Yes, how far?
So that really depends on the pollution species that you want to measure. Yeah, it's very different for methane, from nitrogen dioxide, for aerosols. It's very different depending on the circumstances. So which solar zenith angle, how much light there is. So I think there's not one answer you can give. Anything you want to add to that, Bas?
If I want to give more answers to that question, I would like to understand a bit more behind the question. If you say, what height can you measure? Can you explain a little bit more about what you would like to know?
Well, the question was very simple. Just how far in height can you measure pollutants?
Okay, yeah, I thought so that the instruments, they measure some products like ozone, they measure different heights. We saw that Professor Cruz explained about ozone that is sitting far away from the surface. That's the ozone layer. That is very good because it protects us from harmful radiation, UV radiation. But there's another product that measures the tropospheric ozone. That are two different products of the same instrument. But most of the other air pollutants like NO2 and particulate matter, then the product is a total column product. Meaning you do not know how much of the information is actually at the surface where we live, where the air pollution is harmful, and how much is aloft, higher above the ground. So most products, there are products that are specifically for the troposphere, so this lowest layer where the clouds are, where our weather is, and where we breathe the air. But most products are a total column. And that the translation from total column to surface, you need a model to finally interpret the data.
Great, thank you.
Okay.
Are there more questions from the audience? If go ahead, Carlos.
Yeah, I have a question. This regarding the collaboration between Mexican organizations and TNO. Could you elaborate on the possible modes of collaboration with TNO? Let's say, like, for instance, interchange of researchers. Or are you open to those type of collaborations, like internships of Mexican researchers at TNO and vice versa, internships of TNO researchers in Mexican universities and research centers? Could you give us, or examples of types of collaboration with other organizations?
Yes, absolutely. Yes, we are open to exchange researchers, so that's a possibility. We usually don't do that just for the purpose of exchange researchers, and that normally happens in the context of a joint project or a joint development that we do. So that can be an academic cooperation. For example, we work with a university that developed mathematical methods that allow us to assimilate the satellite data into our model. And we can use the results of that research to improve our prediction systems and we can exchange researchers. It also happens more on the application side. That is the, let's say, 80% of our activities are really application driven. So, for example, we work with local policymakers in Germany, in the Netherlands, in other European countries to develop prediction and monitoring systems of air pollution and emissions using greenhouse gas data. And as part of that cooperation, we provide trainings or people come to TNO to work with us for a while. Some of these cooperations are between us and a government, but sometimes they also include the university. So we have three parties. Sometimes they can also include industry. So you have 4 parties. In particular, space agencies can play a role here. We do a lot of cooperations with the Netherlands Space Agency, NSO. So that is also a stakeholder that can be involved. So I think there's lots of possibilities. I think the main interest of TNO is to see if we can team up with organizations in Mexico to help you use Tropomai or other satellites to tackle the issue of air pollution and greenhouse gas monitoring in your country, where we can make available tools, knowledge, and people, where we would look at you to define the local problems and the funding, so we can jointly address the issue in Mexico, where knowledge transfer plays a key role, because we're not a commercial organization. So while we have all kinds of knowledge and tools, we are not looking forward, we are not here to sell you that product. So Lotus Jules is an open source product. We can transfer technology to you, because in the end, we want to make sure that the knowledge stays in Mexico, so you can keep working on it. And we keep developing new innovations, because that is in the end our mission.
Thank you very much.
Thank you very much. I'm sure that Dr. Guadalupe Galindo in San Luis Potosí State is very interested in this possible collaboration with TNO. They are using already measurements of different carbon and other contaminants, pollutants. So, guys, you want to give way to the follow-up actions?
Yeah, well, I assuming that we are the Q&A session has ended. Are there no more questions from the audience? No questions?
No,
well,
that seems so.
So then we can proceed to explore ways of collaboration between TNO and the Mexican Space Agency and other institutions. We already know that we can develop joint projects in the areas of analyzing data and also using the Tropomai instrument. But also I would like to explore if we can join forces with TNO in the development of optical instruments, because at the Mexican Space Agency we have a center dedicated to development of small satellites, and one of our main interests is to develop our own Earth observation satellite. Actually, right now we are in the process of developing what we call the Latin American satellite, which is an instrument, a 3U CubeSat with an optical payload. It's already designed, but we would like to explore the possibility of joining forces with TNO engineers and develop our own optical instruments. But that's one possibility of collaboration. And also, I would like to mention, probably you already know that Mexico is leading an effort to operate an already created Latin American Space Agency, Latin American and Caribbean Space Agency. This new space agency is going to follow the model of ESA. And about 10 days ago, there was a ceremony in Mexico City where 18 countries from Latin America signed an agreement to join the Latin American and Caribbean Space Agency. So I'm pretty sure that with this development, we will start working on more ambitious projects, especially in the area of instrument development to monitor the region in different aspects. So one of that I want to put that on the table, because that could be a very real possibility.
Yeah, I think that's a nice idea, and congratulations with the Latin American initiative to set up a space agency. I think that will indeed allow you to undertake more ambitious initiatives. TNO already helps other countries with instrument developments. For example, we support NASA with instrument development, but also the Chinese Space Agency. So I would say across the world, people come to us for support, and that can be many supports. Sometimes people ask us to review a design, and we have about 200 people working in optical instrument design, which is a very big group for such a specialized activity. And we just take our specialists and we can, help providing ideas and suggestions. Sometimes people come to us and say, can you design a special part of our system because it requires certain capabilities? Sometimes they come to us to ask for testing, or sometimes they come to us for calibration of the instrument. And with so many years of experience, we often can help, not always, but if we can, we are happy to do that. In other cases, we do co-developments where we really say from the beginning, okay, let's team up and jointly develop a mission or an instrument. And what I see, especially now with the somewhat bigger CubeSats, is that it becomes attractive to team up at mission level. To say that you do a mission that is sponsored by 1 or 2 countries or 2 space agencies to speed up the development. So there's all kinds of possibilities, and we already do it. And in principle, we are more than happy to work in Mexico. Absolutely.
Thank you very much. Yeah, I would like to mention that I mentioned one of the centers, the space centers of the Mexican Space Agency, which is dedicated to image processing and small satellite development and rocket design. But we have another center located in the state of Zacatecas that is specialized in communications, in space communications, and that center can be complementary to the efforts of TNO in terms of designing communication systems for space applications. So we offered you this collaboration, and we have the head of this center here at this webinar, Dr. Jorge Flores. So I'm sure he will be glad to discuss with you in the future possible avenues of collaboration in this important area of space technology.
Well, I'll be happy to connect you to my colleagues who work in satellite communication. We have a big team in optical SATCOM and also a team in RF SATCOM. The optical SATCOM team is bigger. The RF team mostly works in the military domain. They're part of the defense unit of TNO, but I'm happy to connect you and to set up that conversation. Absolutely.
Thank you very much. So one of the things that I would like to explore briefly, there's not a lot of time, is what could be the next steps in this collaboration that we are initiating right now. Do you think that it will be suitable to have a more specific webinar direct towards specialists, or what do you suggest in that regard?
Yes, I think that there's many ways to go about this, but after many years of experience, I think one of the most powerful ways and often the most successful ways is to when we focus on tropomai. So I think we can have conversations about instruments and communication. But if you look at the air pollution and the greenhouse gases, it would be interesting to know from you where you see challenges, where you think the satellite data can help you. And if we identify one or two of these challenges, we can do a follow-up to see if indeed satellite data can provide a solution on top of what you already have in your country in terms of ground infrastructure for modeling and capabilities on atmospheric modeling. And we can see if technically there can be a solution. So first the problem, then see if it technically works. And in parallel to that, we then have to look at how much budget would be needed for it and how it can be funded. Where normally TNO can provide knowledge and people for such a cooperation, but to develop the solution for Mexico, we would need funding from the Mexican side. So if we have a problem, we can find a joint solution and there is funding. We set up a, let's say, pilot project to see if we can work together. And if that goes well, then usually, it can grow into bigger things. So I always like to do that bottom up, because then you're working on something practical that will have a real result. So I'm a pragmatic person, so that is the approach I usually advocate. However, there's all kinds of other ways we can discuss as well, like interagency cooperations, government-to-government cooperations, but they tend to take significantly more time.
Thank you. So I think this has been a starting point, having this webinar, this excellent webinar. It is being recorded. It's going to be, we will use this webinar as a promotion tool for this collaboration, because I'm sure there's more organizations in Mexico that will be very glad to know about these opportunities of collaboration with TNO. So we will be promoting the webinar, and we will be talking to other stakeholders in Mexico, seeing if they have interest in joining forces with the Mexican Space Agency to work with TNO.
Okay, fantastic. Maybe from our end, if maybe it would be good to be in contact with you again in a few weeks' time to see what the response has been on the webinar, and if indeed you think there are air pollution or greenhouse gas challenges that we can already today start addressing with you. And also we could then discuss what other meetings could be about on the instrument development for optics and communication.
Okay, yeah, I have one idea to get more information from the audience. And so I would like to submit a survey to the people that attended this webinar. So maybe we can design between TNO and the AEM the questions for the survey. It doesn't have to be a very, very complicated or convoluted survey, just probably 5 questions to get a feeling of what are the areas that the participants are interested in this collaboration. So I can start with a first draft of the survey, and I will send the survey to you, and then we will send the survey to the participants, and in that way we can have some more information about the needs and aspirations and possible projects that we can develop with our partners. So
yeah, sounds good. Nice idea. I like it, and let's do it like that.
Okay, so we will do that, and Mario. So I think there's no more time for questions and conclusions.
Okay.
So I would like to end this event on behalf of the Mexican Space Agency. I'm very glad that we organized it, and we would like to thank our friends from TNO, Paul, Max, Beth, Wolfgang, for their effort in preparing this wonderful webinar on the use of satellite technology to monitor air quality and greenhouse gases from space. I think it was very fruitful, and we would like to continue collaboration with TNO. And in the near future, we will be in contact with you, and of course, we would like to establish partnerships and develop joint projects, but we will need to find the areas of common interest in order to develop these partnerships. Of course, for the Mexican Space Agency, it's a priority to explore the development of remote sensing instruments and to use data from the Tropomai instrument also, and also join forces with other countries in Latin America and the Caribbean to explore the development of Earth observation satellites for remote sensing of different variables, and so we will come back to you, and we will keep the communication. And I would like also to thank Dr. Xochitl Cruz from the Institute of Atmospheric Sciences of UNAM for her contribution to this webinar. We would like to see more Mexican specialists in future events, and we would like to share, also data with you and to explore other ways of collaboration in space technology and space science. So that being said, I would like to also to thank our audience, all the persons that attended this webinar in this Zoom meeting room, and also the persons that are watching this webinar in our YouTube channel. The webinar is recorded, so I'm sure that it will be viewed in the future by more persons, and we will be happy to know their reactions to the webinar and to hear from you. We would like to hear your comments in future webinars from the Mexican Space Agency, and specifically with TNO. So thank you very much. Thank you, Mario. Thank you, my colleagues from the Mexican Space Agency, for having attended this wonderful event. And if you want to say something, colleagues from TNO.
Well, yes, absolutely. Well, thank you for organizing this wonderful event, for hosting it, for the fruitful initial discussion we had with you, and I think the excellent facilitation you provided today with the very kind words of your Director General and the good technical discussion, such a large audience. I think I speak for all of us when I say it really has been a pleasure. And we look forward to discussing next steps with you.
Thank you very much.
Great. Well, if there is nothing else to talk about, we can finish this presentation and thank all the participants and the people behind scenes that help us do this wonderful presentation. Thank you very much.
Thank you very much.
Thank you. Bye-bye.
Thank you very much.
Bye-bye.
Thank you very much.